Okay, let's settle down. Okay. So today we are going to talk about secret sharing, finite fields, and erasure codes. All right? Okay, so back in the 1950s and 60s, okay, so back in the 1950s and 60s, I don't know if you know, there was this period of intense Cold War with what was then the Soviet Union, and there was this question about nuclear weapons and under what circumstances they could be used. You know, so once you have such powerful weapons, you have questions about who should deploy them. You know, is it only the president who can do that, or under what circumstances can that authority be delegated to somebody else? And if so, if you delegate that, do you really want somebody to have the power to destroy the world? And so there were actually instructions put together for how this authority would be delegated and to whom and under what circumstances. And so, you know, well, the idea was that no one person would have the information to actually push the button. And so there were these secret codes that were to be used, but the point was to make sure that, you know, among the officers who were authorized to do this, no single one would have the information necessary to actually set off the device, you know, to actually launch a missile. So we can abstract this question about how to conduct this, you know, how to give out this information in such a way that no one person has the information as the task of sharing a secret key. Okay, so your secret key is a sequence of bits or of digits or of alphanumeric characters, and now you want to share it among many people. So say you're trying to share it among 5 officers, and what you want is all 5 should be present and agree on launching the missile before they actually can do that. Okay, so you give each of them a piece of the key. So now how do you do that? Well, here's an easy way. What you do is you take this key and divide it into 5 parts and hand one of them over to each one. Okay? So there are a couple of reasons that this is not a satisfactory solution to this secret sharing problem. Okay, so here are 2 reasons. The first is that all the officials whom you give the key to have to be present. You know, so that was a requirement. If you're going to hand over the shares of the secret to 5 officials, then all 5 have to be in agreement before you can authorize the launch. Okay. But now, what if you wanted to authorize 10 officials and you wanted to say, if any 5 of them are in agreement and happen to be there at that time, right? Happen to be present at that time, then they can go ahead. They are authorized to do that. Right? That's a different requirement. You know, so now what would you do? Well, you could try to divide this key into 10 parts and give, you know, so you could say, well, let's divide it up into whatever 10, however many parts we want, and then hand one over to each. Well, now if 5 of them get together, they might still be mystified about what the secret key is, and they wouldn't be able to carry out the instructions. There's a second flaw in the solution, which is, well, what happens if 3 of these officials go rogue? Okay? So you hand over one, you know, so you've divided up the key into 5 parts, and you've handed over one share to each official, but now 3 went rogue. Okay, so they still don't have enough information, but they have partial information. They know what 3/5 of the key looks like. And maybe now, based on that and some other information, they can reconstruct the entire key. So you've still compromised the security. If you thought the key should be, 200 digits long, well, now it's down to 60 digits. And maybe that's just not long enough for your purposes, because otherwise maybe you'd have picked 60. Right? So what you want to do is this. So you want this kind of a secret sharing scheme. So it's called a KN scheme. Okay, so you have a secret S. It's some string that you want to keep secret. You want to distribute it among K players. These are among N players. So these are the N officials. Okay? So you give each of these N officials a share of the secret. What are the properties we want? We want that any K of the officials, so think of N as 10. So there are 10 officials in all. K is 5. So as long as 5 of these officials get together, they can reconstruct the secret. Okay? But then we want this additional property that if you have any coalition of K minus 1, so even if 4 officials try to get together and they try to reconstruct the secret, they have no more information than somebody who wanders in off the street. Okay, so the fact that they had 4 shares of the secret gives them absolutely no information at all about what the secret was. They're as much in the dark as anybody else out in the country. Okay, so if you think about it, this is a pretty remarkable property to have. Yeah? So what's remarkable is both that any subset of 5 of them, any 5 out of the 10 can reconstruct the secret, but then any 4 of them try to do it, and they have no idea. Right? The secret could be anything at all. They have no more information than when they started. Okay? So what's remarkable is that there's a way to do this. And this is called Shamir's secret sharing scheme. Shamir as in RSA, right? S? That's Shamir. Okay? And this secret sharing scheme is based on polynomial interpolation. Do you still have a question? No. Okay. Yes?
You just pick a value for K, or just pick a
It comes with the problem. So imagine you're the president. You've figured out how many officials should have access at all. Maybe there are 10. So there are 10 officials, and then you figure out in order to have adequate security, you want that at least 5 of them should be present. So that these choices N and K are dictated by the problem at hand. Okay. Then you feed NK into the secret sharing scheme. So you tell Shamir, I want a secret sharing scheme with N equal to 10 and K equal to 5. Can you please provide me with a way of doing this? And Shamir tells you, well, look, it doesn't matter. You give me any K and N, I'll tell you how to do it. Yeah? Okay. All right. So how do we do this? Well, we go back and remember polynomials, right? What are the properties of polynomials? So last time we said polynomials have 2 very beautiful properties. One is that any non-zero polynomial of degree d has at most d roots. So what's the root of a polynomial? So remember, if you have a polynomial x to the d, well, a naught x to the d plus a1 x to the d minus 1 plus so on plus a sub d, and you want to know what are those values of x such that this polynomial evaluates to 0. Then the values of x for which this polynomial evaluates to 0 are called the roots of the polynomial, and the claim is that a polynomial of degree d has at most d such roots. The second property says, if I tell you that I'm thinking of a polynomial of degree d, and if I happen to let slip what the values of this polynomial are, what this polynomial evaluates to, at d plus 1 different values of x, then if you know enough math, the polynomial is no longer secret from you. You can reconstruct what the polynomial is. You can reconstruct all the coefficients a naught through a sub d. Okay? So now, before we proceed, let's try to understand what are these coefficients a naught through a sub d? Where are they chosen from? Okay, so let's write out some polynomials and let's see where they're chosen from. So for example, you could have the polynomial 4x squared plus 3x plus 1. That's a perfectly nice polynomial. You could have the polynomial 2.5 x cubed plus 3 over 4 x squared plus 2x plus 9. That's a perfectly nice polynomial. So the coefficients can be rational numbers. They could even be real numbers. So you could have pi times x cubed plus e times x squared plus 2x plus 4.5. Right? So all this is fine. You know, the coefficients can be chosen from the rationals, the reals, or even the complex numbers. Now, we don't really want to think of the coefficients as coming from the natural numbers or the integers, because the properties of polynomials that we used to prove these two crucial properties, right? The fact that polynomials of degree d have at most d roots, and that the fact that you can interpolate polynomials. The properties that we used were that we can add, subtract, multiply, and divide these coefficients. Okay, these are the properties that we used. And so if you are told that the coefficients happen to belong to the natural numbers, then we can't subtract them, right? In general, you cannot take the difference of two natural numbers and hope to get back a natural number. Or even if we enlarge our set and say it's all integers, we can't really divide integers. So if we divide two integers, in general, we don't get an answer which is an integer. But if we work with the rationals, then certainly the sum of two rationals is rational, the difference is rational, the product is rational, and the ratio is rational, provided we don't try to divide by 0. Right? The same is true for the real numbers. The same is true for the complex numbers. And so what these are called, in algebra, they're called fields. Okay, a field is a set of numbers which has this property that you can add them, they satisfy the usual properties of addition, subtraction, multiplication, division that we'd want. And they're always well defined unless you try to divide by 0. So that's the only exception. If you try to divide by 0, you're out of luck. But other than that, everything works as normal. Right? So what do I mean by everything works as normal? What I mean is you can add two numbers. Moreover, a plus b is the same as b plus a. Right? It's commutative. A times b is the same as b times a. A times b plus c is a times b plus a times c, so it's distributive. So they are the usual properties you expect from addition, subtraction, multiplication, division. They all hold, right? This is called a field. Okay? Now, it turns out that there's another kind of field that we can have, which is not infinite like the rational numbers or the real numbers. Okay? So we can also look at what are called finite fields. So for example, if you look at the numbers 0, 1, 2, 3, and 4 under addition, mod 5, multiplication, mod 5, etc., subtraction, division. These form a field. Okay, why is that? Well, because, when you are working mod n, addition is always fine, right? You add two numbers mod n, what do you get? You get a number mod n, right? How about subtraction mod n? It's always fine. It's always okay to subtract mod n. What about multiplication mod n? If you multiply two numbers mod n, you always get a number mod n. Okay? Division, this is a bit, that's a bit, suspect. And so as long as you choose n is prime, then division is okay. Because as long as you don't divide by 0 mod n, you're fine, because if n is prime, any number which is not congruent to 0 mod n is relatively prime to it. And so it has a multiplicative inverse, which is another way of saying you can divide by that number. Right? Okay, so the main lesson to learn from all this is, if we are going to be working with polynomials, and if all we care about is those two properties of polynomials, then we may as well be working modulo a prime. It's just as good for our purposes. We can count on those two properties, because those are the, because to prove those two properties, all we used is the fact that we can add, subtract, multiply, divide those coefficients. We can do that if the coefficients come from a finite field. Okay? Okay, so what do we have in mind now? So what we have in mind is that we are given polynomials where the coefficients come from a finite field. So maybe we are working modulo 7. Okay? And perhaps our polynomial might be x squared plus 2x plus 3. Okay, so that's one polynomial, let's say a of x. And we have another polynomial b of x equal to 2x squared. Maybe let's make it 3x plus 5. Okay? And so now, what's a of x plus b of x? So what we're going to do is add them as polynomials, except remember the coefficients are numbers mod 7. So when we add them, we'll get x squared plus 2x plus 3x is 5x plus 3 plus 5 is 8, which is 1. We could also look at a of x divided by b of x. Okay, so how do you work this out? So we could do long division. We could say we have x squared plus 2x plus 3. We want to divide by 3x plus 5. Okay, so how many times do we have to, what do we have to multiply 3x plus 5 by to? Okay, so we want to divide 1 by 3, right? So what's 1 over 3 mod 7? 5, right? Because 3 times 5 is 15, which is 1 mod 7. So we want to multiply this by 5. When we multiply this by 5, we'll get 15x squared. We want to multiply this by 5x, right? So if we multiply this by 5x, we'll get 15x squared, which is x squared, plus 25x. 25x is what mod 7? Plus 4x. So you subtract, and you will get minus 2x, which is 5x plus 3. Okay, you get the point, right? So now how do we cancel off the 5? We multiply by 5 over 3. What's 5 over 3? Sorry, what was 1 over 3? 1/3 was 5, so we want to multiply 5 times 5, which is 25, which is 4. So you get 4x plus So, sorry, what did we do here? We wanted to multiply by, so we multiplied by 5 divided by 3, which is 5 by 3 is 4. So 4 times 5 is now 20, which is whatever, it's 6. Sorry, we should have got a 5x here, right? And then we get something, minus 3, which is 4. Okay, so you get the point, and I should have filled in the things here, but does anyone remember what we chose? I'm sorry? Plus 4. Okay, so what we are saying is x squared plus 2x plus 3 is 3x plus 5 times 5x plus 4 with a remainder of 4. Okay, so you get the point that when we work with polynomials over a finite field, nothing different than what you've seen before, right? You just work with polynomials the way you work with polynomials. You work with modular arithmetic the way you've been working with modular arithmetic. It all works out. Yes?
Can you explain why 1/3 is 5?
Well, why is 1 over 3 equal to 5? So 1 over 3 mod 7, you could actually do extended GCD, but you could also observe that 15, so what do you want to do? You want to divide 1 by 1 mod 7 by 5, right? But 1 is not divisible by 5. But 1 is the same thing as what? It's the same thing as 15, as 8. 8 is also not divisible by 5. So sorry, it's not divisible by 3. But then you go on to 8 is also, 1 is the same as 8 is the same as 15. Right? So 1 is congruent to 8 is congruent to 15. Well, we got to 15. 15 is divisible by 3. Right? So what's 1 divided by 3? It's 15 divided by 3, which is 5. Okay. If you did extended GCD, you'd get the same result.
What did your numbers be? 7 and 3?
Yes. Yeah? Okay. Yes?
So when you do a of x over b of x on 7, would the answer just be 4?
When you do what?
A of x over b of x on 7.
What's A and B? Oh, what's A of x divided by B of x? So remember when you divide polynomials, what you get? You usually get a quotient and a remainder. So what do you get? Well, let's write it out. So you'd get A of x equal to B of x times some quotient. So what's the quotient polynomial? It's 5x plus 4, right? It's what we wrote up there. And then there's a remainder. So remember, this is a degree 1 polynomial, so you expect the remainder to be degree 0, which means it's a constant. So what's that constant? It's this one, so this is the remainder 4. Right? So that's your division by polynomial. You divide this polynomial by this one, you get a quotient, which is a polynomial of degree, right? Whatever it needs to be, the difference. And then you get a remainder, which is a polynomial of degree necessarily at least 1 less than that. Yeah? Yes?
Something works if it's a prime number, right?
I'm sorry?
If it's a mod of a prime number?
Yeah, that's when it works. Yeah. So since you need to divide and all this, we need to be sure that we can divide by any number which is not 0. And for that, we need that it's a prime. I'm sorry? What do you do with the remainder? You just write it down. I mean, if your remainder happens to be 0, then you can say, well, this polynomial divides that one. If there's a remainder, there's a remainder. It's what happens when you divide one integer by another. Right? If there's no remainder, then you say, well, this number is divisible by that one. If there's a remainder, you'll say, well, n equal to m times q plus are, right? That's what you said. Yes.
So A was x squared plus 2x plus 6.
Yes.
Then that means that would be factorable by 5x plus 4,
That's right.
even though it's not like that normally. So
It's-
you could factor things in odd ways. in
That's right.
finite fields.
That's right. Yeah. Yes. Yeah. Okay. So let's get back to where we started from. Right? So what we wanted to do was secret sharing. So remember we have one secret in mind, S. Okay? S is some number. Okay, so now since S is a number, we can also write it modulo a prime. So we pick a prime larger than S, and we say the secret is S mod P. Okay? All right, so now we also want to deal this secret out to n officials in such a way that any k of them can reconstruct the secret. Okay? So what should we do? Okay, so what we want to do is we want to make sure that P is also larger than n. Okay, so here's how we're going to proceed. So let me show you what we're going to do. So let's do an example. So suppose that our secret S is, let's say, 3 mod 5. Okay, I'm working with a small prime because the calculations are going to get, I'm just going to do these calculations, extempore, and the chances are not very large that we'll get them right anyway, and so let's not chance luck too far. Okay, so let's say that's what that's what S is. Let's say that n is 4, so we have 4 officials, and we want k equal to 3. So any 3 of them should be able to figure out the secret. So any 3 should be able to reconstruct. Okay? All right. So now, here's the idea. The idea is we are going to create a polynomial. Okay, so we are going to pick a polynomial. So we are going to choose a of x such that a of 0 equal to s, meaning it's 3. Okay, so we are going to be working mod 5 in everything, right? So we'll work mod 5. We'll choose a of 0 equal to s, which is 3. And now we are going to choose this polynomial at random. Okay? And then to these 4 different officials, we are going to hand them the value of this polynomial at 1, 2, 3, 4, and 4. Okay, so to official 1, we give a of 1. To official 2, we give a of 2, and so on. Okay, is it clear what we are doing? Okay, so first of all, how do you pick a random polynomial with such that a not equal to s? Okay, sorry, but let's see. What degree do we want to pick this polynomial of? So, what should the degree of this polynomial be? Okay, so remember the key property that we want is any 3 of these people should be able to reconstruct S. But so what do each of these officials have? Each of them has the evaluation of this polynomial at a particular point. Okay. What does our basic property say? It says that if you have a polynomial of degree d, then you can reconstruct the polynomial by looking at its value at d plus 1 points. So we want d plus 1 to be equal to 3. So you want d equal to 2. Right? So what we want is a polynomial, the degree of a of x equal to k minus 1, which is 2. Okay, so now what our goal is we want to pick a random polynomial of degree 2 modulo 5 such that a of 0 equal to 3. So how do you do such a thing? Yeah.
Can you just make a second degree polynomial and then put the coefficients at some random mod 5 integer and then evaluate the polynomial at 1, 2, 3, and 4?
Yes, good. So what we'll do is we'll say a of x is a naught x squared plus a1 x plus what? Plus s, right, which is 3. Okay? Mod 5, right? Okay, so now we want to pick a random such polynomial. So we just choose a naught to be a random number between 0 and 4. So just pick it at random, pick a1 at random. So that's our random polynomial. Okay? So we pick that polynomial and then we evaluate it at x equal to 1, 2, 3, 4, and we hand those shares across to the 4 officials. Okay, so shall we pick random numbers? So what's a naught? 4. Okay, so we pick it at random, so it's 4x squared plus 2. 2x plus 3. So this is our polynomial. Okay? So now officials 1, 2, 3 are, 3, 4 want to know what their shares are. So official 1 gets 4 plus 2 plus 3 mod 5, which is 4, right? Official 2 gets 4 times 2 squared plus 2 times 2 plus 3, which is what? This is, the 4 is minus 1, right? So it's this is minus 1 squared, which is 1. This is minus 1, so that's just 3. 3 gets 4 times 3 squared plus 2 times 3 plus 3, which is what? Again, 3 squared is minus 1, right? 9 is minus 1 mod 5, so you get minus 4 plus 3 2s are 6 is 1 plus 3, which is 0, right? And official 4 gets 4 times 4 squared plus 4 times 4 plus 3, sorry, which is, oh my God, it is just 3, right? Oh, it's 2 times 4, sorry. Okay, so 4 times 4 squared is minus 1. 2 times 4 is minus 2. Plus 3 is 0. Is that correct? So I'm doing this fast. So you know, if I'm doing it incorrectly, you should know. Somebody should catch me, right? So it's okay? Yeah? Okay, good. So now these are the shares of the secret that we've given out. So let's see, it's 4, 3, 0, 0, right? So oops. Let's go forward. So it's 4, 3, 0, 0. So official 1 gets 4, official 2 gets 3, official 3 gets 0, official 4 gets 0, right? And now 3 of them get together and they're trying to reconstruct the secret. So which 3? 1, 3, and 4. Okay, so 1, 3, and 4 get together and they want to reconstruct the secret. So let's see if we can help them do that, right? Okay, so what do we want? So we want to create a polynomial which, so here's our picture, right? So we want, here's 0, 1, 2, 3, 4. So we want a polynomial of degree 2, which takes on, that's 1, 2, 3, 4, right? So which takes on these values. At 1, it has value 4. At 3, it has value 0. At 4, it has value 0, right? We don't know what its value at 2 is, because only 3 officials got together to try to reconstruct this. Okay? Okay, so now we do this. Okay, so let's make up a table. We say, well, what are we interested in? We are interested in the values at the points x equal to 1, x equal to 3, x equal to 4, right? And now let's look at a few different polynomials and see what their values are. Okay, so we'll try a few polynomials which will be helpful to us. So let's try the polynomial x minus 1 times x minus 3. So what are its values at 1, x equal to 1? 0. What about x equal to 3? X equal to 4? 3. Right? 3? Yeah. Okay, let's try x minus 1 times x minus 4. What are its values at these 3 points? What's its value at x equal to 1? X equal to 3? Minus 2. Minus 2 is? X equal to 4? How about x minus 3 times x minus 4? At 1, it is 2 times 3, right? 2 times 3, or minus 2 times minus 3, which is 6, which is 1. 0, 0, right? Is everyone clear why I chose these polynomials? Is everybody clear why I chose these polynomials? Because I wanted them to be 0 at every point, every value of x except 1. So how do you do that? You just take x minus each one of them. Right? You know this joke, right? Evaluate x minus a times x minus b times x minus c times so on up to x minus z. 0, right? Because okay, all right. So now, given that we've figured out these polynomials, how do we solve the problem that we had at hand? So we wanted to compute a polynomial a of x, which has this behavior, that at 1 it has value 4, at 3 it has value 0, and at 4 it has value 0. So how do you do it? Well, we are going to add together these polynomials. Okay, it was very unfortunate. We picked everything at random. We got zeros here, so what can you do? Right? But so what are we going to do? Really? Is it like that? So it's just 4 times x minus 3 times x minus 4? Is that what we want? Right? So what do we want? We want it to have value 4 at x equal to 1 and 0 everywhere else. Right? So if we just choose 4 times this polynomial, we are done. Yes? In general, okay, so in this case, our polynomial is just 4 times x minus 3 times x minus 4. I don't know, is this the right polynomial? It is 4 times x minus x squared minus 7x. Minus 7x is? Plus 5, right? It's plus 3x. Minus 12 is minus 2, which is plus 3. So you get 4x squared. I'm sorry? Oh, sorry, it's plus 12, so it's plus 2. And so you get 4x squared plus 12x, which is 2x, plus 8, which is 3. Is that what we started with? Well, let's... 4x squared plus 2x plus 3, right? 4x squared plus 2x plus 3. So that's the reconstruction of the polynomial. So once you have the polynomial, what do you do? What's the secret? It's just this, right? It's just 3. Okay, so that's secret sharing. That's okay. So by the way, just to carry this out, let's let me just erase this answer here so I get some room here. But okay, so let's okay, so let me even write it out here. What was the it was 4x squared plus 2x plus 3. Okay, so now let's just to go over it, make sure that you understand how one does interpolation. Let's say that we had a different value at 3. So what would you like? So let's say we were doing let's say that our polynomial had, we were trying to interpolate a different polynomial. So let's say it was I'm sorry? 1 at 1? 1 at 3, and
1 at 4.
You want 1 at 4? 2 at 4? 2 at 4, 1 at 1. Okay, let's say we are trying to interpolate this blue polynomial. So what do we do? Okay, so what we are going to do is to get the value 1 at 1, we can choose this polynomial, right? X minus 3 times x minus 4. So now we know that so far we have value 1 at 1 and 0 everywhere else. Then we add to it a polynomial, which is something corresponding to this. So it's some multiple of x minus 1 times x minus 4. So what multiple do we want? 1/3, right? Because this has value 3 at 3 and 0 everywhere else. We want value 1 at 3 and 0 everywhere else. Yeah, so we want to take 1/3 of this polynomial. What's 1/3? 2. So we multiply by 2. Then we take this polynomial, x minus 1 times x minus 3. This has value 3 at 4. We want value 2 at 4. Right? So how much should we take of it? Right? 2 divided by 3. What's 1 over 3 again? 1/3 was 2, so we get 2 times 2, which is 4. Okay, so that's the polynomial we want. Okay? Is everyone happy with that? Okay, now, does anyone want to see the ugly formula that represents this calculation? Do you actually understand this formula? How many of you actually understand that formula? Anybody who doesn't understand the formula who wants to? Okay, well, at this point, I'm happy if you go home, you read through the notes, it might make sense to you what the formula is saying. Okay? Yes.
I have a question sort of related to the idea of secret sharing in a finite field.
Yeah.
It sort of seems like a really bad idea to me because when you use a finite field, you're restricting the values of secret to be so someone can just try and guess all the values. Why would you put it in a finite field?
Okay, so the question is, why did we use a finite field here? I mean, it seems like a bad idea because your possible secrets are now restricted. Okay. Well, so the first thing is, there's no limit to how large primes can be. You can choose P as large as you want. So for example, if you want a 100-digit secret, you can pick a prime which is that large. Okay? So that's the one reason. So it's not a big restriction. But the second reason is we haven't yet addressed this issue, saying that this secret sharing scheme was really secure. So what it means for it to be secure is this. Any coalition of k-1 officials have no information whatsoever about what the secret was. Okay? It turns out that if you use an infinite field, some information is going to leak out. Maybe hard to get at, maybe hard to quantify, but we'll never know. It's sort of a complicated issue, how much information leaks out. With a finite field, we'll prove that no information at all leaks out. So if you have k-1 people, they are completely in the dark about what the secret is. Okay? And that's the main advantage of choosing a finite field. Well, so the people who are trying to reconstruct the secret, so you have k-1 officials, each of them knows what P is, right? They know the prime. Each of them has a share of the secret. So maybe it's the first official. So the first official knows exactly what A of 1 is, right? So you have k-1 such officials, and each of them knows what the value of the polynomial is at one point. The claim is these k-1 officials are as much in the dark about the actual secret as you or I. As far as they're concerned, it could be anything, any number between 0 and p-1. Okay? So we'll show this, right? And that's the really important property that choosing a finite field brings to the table. Yes? Okay, so so far what we have shown is that if you have a coalition of k of the officials, they have enough information to reconstruct the secret. Why do they have enough information? Because it's a polynomial of degree k-1. You can reconstruct the value of a polynomial of degree k-1 if you're given its value at k points. The next thing we want to show is that if you have so the next thing we want to show is that if you have k-1 officials, they have absolutely no information about the secret. Okay, so and the way we'll show that is actually extremely simple. Okay, so here's how we'll show it. Here's our problem in general. Okay, so we have these are k-1 officials, right? Each of them knows the value of the polynomial at one of these points. So this one knows the value of the polynomial here is that one knows it's that one knows that one knows that. Okay? So we have k-1 officials. It's a k-1 degree polynomial. Okay? It's a completely random k-1 degree polynomial. Okay? Now, what can they reconstruct? What can these k-1 officials reconstruct? Well, here's one way to answer the question. What you do is sort of reduce the problem to what you already know how to solve. Right? That's the easy way to go about solving a problem. So what do we know how to solve? We know how to reconstruct the polynomial given the value at k points. Right? Because it's a k-1 degree polynomial. So let's choose a kth point. So which one should we choose? Yeah, let's choose the value at 0. So let's choose the value at 0 to be that. What do we know about the polynomial that goes through all these points of degree at most k-1? How many such polynomials are there? There's exactly one, right? How about if we changed our mind and we said, that's not a good point. Let's shift it over here. What happens then? How many polynomials are there that go through these k points? Exactly one, right? So for every way of choosing the secret, there's exactly one polynomial that's consistent with that choice of secret and the shares that these k-1 officials received. Okay? So there are exactly how many? Exactly p different such polynomials. We are working mod p, right? That's it. That possible secret could be any number mod p, 0, 1, 2, up to p minus 1. So you can come up with p different reconstructions of this polynomial, one for every such choice, right? And each of them is, for all you know, since you picked a random polynomial to begin with, each of them is equally likely to be that polynomial. There's nothing to distinguish them at all, right? So as far as these k-1 officials are concerned, the secret could be anything at all. And so they have no information whatsoever. Yes?
If you have k-2 optional,
Yeah.
you pick 2 points, right?
Yes.
Would it be less?
Would they have less information?
Yeah.
Well, if you have k-2 officials, then you'd pick the values at 2 different points, but one of those 2 points could be the secret. And again, you have, your secret could be whatever it needs to be.
So what I'm trying to say is that if you have k-1 optional,
Yeah.
you always pick 1 point. If you have k-2, you have to pick 2 points.
Yeah.
And if you have a k-1 official, you know more information about the secret than k-2.
Well, the point is, you have at least as much information, but in each case, it's 0. Right? Yes?
Couldn't you make the same argument for an infinite field, though? Because in that case, you would say, well, they need one more point, and that would be out of some infinite set of points, so they still don't have enough information.
Right. Yeah, except how do you pick a random number from an infinite field? How do you pick it uniformly at random? So the way you'd pick a number at random, a real number at random, is you'd sort of you'd have some it would fall off, right? So you'd be more likely to pick smaller numbers than larger numbers, because if you're equally likely to pick small and large numbers, and there are infinitely many of them, then you have probability exactly 0 of picking any one of them, right? And so it gets a bit dicey when you start working with infinite fields. You could, when you're doing cryptography, if you could use it, you wouldn't know how to prove it, but also it would probably not be true. And then, since you are picking it non-uniformly, maybe your adversary would actually exploit that and say, aha, right? So the secret, these coefficients are picked so that they are small with higher probability, and this creates this non-uniformity in what the secret looks like, and it's more likely to be this than that.
Since you're on an infinite scale, small and large become really relative. So small is 1,000, whereas if my adversary could think that's smaller than 100.
Well, it's you're left guessing about what you got and what you didn't get. Here you know what you got, which is you have absolute certainty. Yes? Yes?
Can you say your finite field is a subset of the infinite field?
I'm sorry?
Can you say your finite field is a subset of the infinite field?
In what sense a subset?
Like you can have a finite field inside the infinite field.
I think you have to be much more careful about that, because it's not just the numbers but the operation. And the operation is different now. You're not just adding numbers, you're adding them mod 7 or mod 5.
Because if you could do that, then like in the infinite field, there's always a limit that becomes like the numbers problem.
Yeah, but you know, as I said, you can't really embed it in this way because your operations are different now. Yeah? Yeah.
Can one person trick the other ones? Like, let's say we have K people.
Yeah.
One person wants to trick the other ones that the secret is a number, like one higher than the actual figure, and actually get the actual figure himself.
I'm sorry, so you're saying, is there a possibility of, if the players themselves are dishonest?
Yes.
Or how do you deal with dishonest players in this? Very good question. It'll be either a homework problem or an extra credit problem. Okay, so you have to depend upon error correcting codes for that. But since both error correcting codes and secret sharing use polynomials, actually there's a very clever way of combining the two. Yeah? Yes?
So if you have, let's say, 10 officials,
Yeah.
then technically we can just use mod 3.
Mod?
We can just mod the whole thing. Can you list the 3 universe?
In a what universe?
Mod 2.
Mod 2? No, if you have 10 officials, then you want your field size to be larger than 10. Because you want to, each official is to be given a different share of the secret. And a share is an evaluation of the polynomial at a different point in the field. So if you're only working mod 2, then you have only 2 points in the field. So you can have only one official, because at 0 you have the secret, and then you have only one other place you can evaluate the polynomial. So you have only one official.
Okay, so it can be great, so it has to be at least equal to.
I'm sorry?
So it has to be at least equal to the number.
It has to be at least?
It has to be at least the number of officials we have.
Yeah, so the size of the field has to be at least one larger than the number of officials. Because you need one spot, that's 0, where you're putting the secret, and then you need at least n spots for the n officials. I'm sorry? It could be much larger. Yeah, there's nothing saying that you cannot make the field very large, except that it's more complicated to calculate with. But you can make it as large as you want. Okay, so everyone happy with that?
They could do approximation like P would be so large that it goes to P.
I'm sorry?
So you can make P extra large, and you can make it really teeny.
Well, it would be finite, whatever you make it. Yes? Yeah, it's going to be some finite value. It's going to be a particular value. Yeah, it could be very large, but it's finite. Yes? Okay. Okay, let's see. So, should we take a minute to talk about how was the midterm? No? I'm sorry? So, for somehow the average in the midterm was pretty high. It was about, I'm sorry? Yeah. Well, I would say that's very high. I would say 20 out of 90 would have been very low, but 70 out of 90 is very high. Yes? I'm sorry? Yes. 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 That's the only reaction? Yes.
I didn't like the problems.
What did you not like?
I thought there was too much true, false answer. It's not much thinking.
You'd have liked more thinking? Okay. I'm sorry?
Because there was so much true false, there was no partial credit because there was a justification.
So it's by judging.
So is that generally true that you'd like questions that required more thinking? Yes? Okay, so let me do this. Okay, so by the way, how many of you have taken the survey? Let's do this. I think that I'll add a question to the survey about the midterm, or a question or two. Those of you who have not taken the survey, please do go and take the survey, and it would be good to get your feedback on many things. Those of you who have already taken the survey, I think there's a way you can go back and answer the additional questions. Okay, so if one of you figures out how to do it, please post it on Piazza and let everybody else know how to do it. Okay, and So if you've already taken the survey and if you want to give feedback on the midterm, please do that. Okay? Yes. Yeah. The solutions will be posted. So just to get a it's sort of easier to get this feedback in the survey, but just to get a rough show of hands, how many of you thought it was on the easy side? On the difficult side? Too short? Too long? Just right? Okay. Okay. All right. Okay, good. Good. Okay. Let's do okay, so let's talk about one more application of polynomials, which is called erasure codes. So these are extremely useful objects. Okay, so let me tell you one application of these erasure codes. So they are used in so you know when you're transmitting information over the internet, the way a web page is transmitted is it's broken up into packets. Okay, and then these packets are labeled with their destination, etc. With the packet number, and then they're transmitted. They are sent off into the wild, and then they're collected at the other end. And once you get all the packets, you put them back together, and you reconstruct the information that was being sent. Okay, so it might be that the page that you have got broken up into n packets, okay? Or a file that you were transmitting got broken up into n packets. And now, in order for you to reconstruct this file, your recipient to reconstruct the file, they have to receive all n packets. Right? If any of them got lost along the way, then you have to retransmit the whole thing. Okay, that's one way to do it. Another way to do it is to use an erasure code. Okay? So what do you do in an erasure code? In an erasure code, instead of transmitting the n packets, you actually create n plus k packets. So if n was 100, you don't transmit 100 packets, you transmit 120 packets. Okay? And the property you want from this erasure code is if somebody receives out of these 120 packets any subset of 100 of them. Sorry, there's a question there? Excuse me, do you have a question? No, please do speak up. No? Okay, so so back to erasure codes. So let's say you're trying to transmit 100 packets. Okay? If you're using an erasure code, what you would do is you would transmit a few more packets than you wanted to transmit. So instead of 100, you transmit 120. Okay? And then, if your recipient actually got any 100 of them, so let's say 20 of them got lost along the way, and we don't know which 20, right? But 100 of them got through, then the recipient can reconstruct the original n packets from this. Okay, that's an erasure code. Okay? So it's a pretty remarkable construction. It gives you a lot of fault tolerance. Okay, so instead of having to retransmit, by actually increasing the number of packets to be transmitted usually by a couple of percent. Instead of 100, you transmit 102 or 105. And then you almost never have to retransmit. right? Because you almost always have at least 100 of them get through. Yes?
Does the receiver know the original number of packets? Like, does the receiver know that you sent n packets, not n plus k?
Yeah, so originally you wanted to send n packets. N was 100, right? Now, instead of 100, you create 105 packets. Okay, maybe the 105 packets are your original 100 packets plus 5 more that you've added. Okay? Now, if your 100 packets get through, they get through. You're fine. You know, you don't even need to do anything. But let's say that 4 of those 100 packets got dropped, but you got at least 4 of the 5 extra packets. So now you can put all this information together, and you can do a reconstruction. You can apply a reconstruction algorithm where you can reconstruct all the packets that were dropped. Okay? So when you state it this way, it sounds quite magical, but it follows directly from the properties of polynomials that we've seen. Okay? So how do you do this? Well, so let's say, you know, your packets are what? You know, they're usually, let's say they are 32 bits long, you know, however long they happen to be. So let's say they are 32 bits. So you would pick a prime which is larger than 32 bits. So P bigger than 2 to the 32. Okay? And now you let your packets be numbers mod that prime. Okay? And so now we have n packets. Okay, so what do we want? Well, so remember, this is always our picture. What we do is at x equal to 1, we let the value be the value of the first packet. Okay, so shall we call that C sub 1. At 2, we have the value, at 2 should be the value of the second packet, let's say C2. At 3, it should be C3, and so on. At n, it should be C sub n. Okay? So now, we want a polynomial that passes through all these points. What should the degree of the polynomial be? N minus 1. So we pick a polynomial of degree n minus 1. So let's call that a of x such that a of j equal to c sub j. Okay? So those are 100 points. Those are 100 packets. So now we want to create 5 more packets. How do we do that? Right? So our packets are just the evaluation of this polynomial at these points 1 through n. How do we create new packets? Yeah, just evaluate the polynomial at further points. Right? So we want to create k more packets. So we evaluate at the point at n plus 1, so on up to n plus k. Okay? So these are the extra packets we create. So the extra packets are a of n plus 1, a of n plus 2, all the way through a of n plus k. Okay? And then once you've done this, you just send these n plus k packets off. And now some of these packets get dropped. Right? Maybe these k got dropped. But then we don't care, because as long as we got n packets, what we have is we've evaluated a at n different points, x. Right? As long as we can evaluate a polynomial of degree n minus 1 at n points, we can interpolate and we can figure out what the polynomial is. Once we know the polynomial, we can recover the packets that got dropped. I'm sorry?
What's the actual?
The actual information you want to transfer are the packets. So the packets, So you have n packets, C1, C2, through C sub n. Yeah? And so instead of transmitting those packets, only those packets, what we did was we constructed a polynomial of degree n minus 1 which passes through those points. Right? And then we extended that polynomial out further. Okay? How did we extend it out further? Well, what the condition we needed was p is larger than n plus k. Right? We have to have at least this many points mod p in order to carry out this scheme. Right? P has to be large enough. But that's not a problem here because p is actually pretty large. It's 2 to the 32. There's no problem with that. Okay? And then, okay, so what did we do? We, instead of n, maybe 100 packets, we now transmit 105 packets. So k is 5. So we transmitted these 5 extra packets. And now what we're claiming is if any of these packets got dropped, we still have interpolation, polynomial interpolation. And because of that, we can fill in these blanks. And the way we fill in these blanks is not directly, but by first reconstructing this polynomial A by interpolation, and then evaluating the polynomial A at these missing packets, at these missing points, to figure out what those missing packets were. Yes?
So you have n packet and you want to reconstruct the information. It's just going to be you the polynomial and then
You what?
if you want to get the original information out of the n package,
Yeah.
you just review the polynomial and then evaluate it.
Exactly. So you're going from the n received packets to reconstructing this polynomial. We know we can uniquely reconstruct it. Then we evaluate it at the missing points, and we've reconstructed the missing packets. Yeah? Okay, now, in practice, it turns out that doing the scheme exactly as it's presented here is not efficient enough. Okay? So a lot of work has gone into trying to make these schemes much more efficient. Right? So this is a vast subject. It's a vast and beautiful and very useful subject. Okay? On the other hand, in principle, if you're thinking conceptually, this is all you need to know. Right? So, all that extra amount of work just goes into putting in the bells and whistles, which make this scheme much, much more efficient, both in terms of encoding the packets as well as decoding and reconstructing the packets which are missing. Right? So you can do everything in nearly linear time and in such a way that you can do it on the fly. And these are at this point extremely well developed algorithms, very clever algorithms. But the theory of them is much more advanced. In terms of the basic theory, I mean, this suffices to give you the framework for what's possible. Right? From here on out, it's just a matter of working through and finding cleverer and cleverer schemes for actually reducing the number of calculations required to do this reconstruction. Yeah? Yeah, any questions? Yes. Yeah, so again, remember, okay, so remember what we said. If you have fewer than n points, if you have a degree n minus 1 polynomial, it's all over. You cannot reconstruct the value at a given point which you do not have. Right? So that's unfortunately something that's true. In fact, we can sort of do a calculation. So if you are working mod p, right, and if you have a polynomial of degree d, and you have the values of the polynomial so if the number of points at which you know the value of the polynomial is d plus 1, then how many polynomials are there that are consistent with this information? There's exactly one, right? Now what if you knew the values only at d points? How many polynomials are there? Well, you can now choose the value at one point completely freely, right? And for each way of doing that, there's exactly one polynomial. But how many ways are there of choosing the value at one point? P, right? So there'd be exactly P such polynomials. Now what if you knew the value at d minus 1 points? P squared, because you have two free points now. Any two points that you want, you can choose, and then you can let the value be whatever you want. So you get exactly P squared. D minus 2, P cubed. You see the pattern, right? It's exactly sort of, it goes exactly according to form. Now let me say one other thing. Okay, so the one other thing, so please listen if and only if you won't be confused by this. Okay? So I claim that as long as you don't go above x to the p minus 1, any two polynomials you write down are distinct. If they look distinct, they are distinct polynomials. But if you go above p minus 1, then you can write down two polynomials which are the same, even though they look different. So if you're working mod p, as long as the degree is less than or equal to p minus 1, all's well, right? So you don't need to worry about anything. Once you go above p minus 1, then things start happening. So what starts happening? Fermat starts happening, right? So x to the p is always congruent to x mod p for all x, right? Which means that x to the p minus x, this polynomial, is the same as the zero polynomial. Okay? Once you have that, you know that x to the power of p minus x plus 1 is the same as the polynomial which is 1. X to the power of p minus 2x is the same as minus x. So you get all these polynomials which turn out to look different, but they are the same, right? So what's the moral of the story? Stay below p minus 1, right? So go up to p minus 1, but don't go beyond. If you go beyond, then think very carefully.